was like, oh no, how am I gonna see?
Hi. I hope everyone. I hope you all can hear me. It's not clear working, but I hope everyone can hear me. Okay. Good afternoon, everyone. This room seems a little tight, but I am sure you can accommodate people who are registered. All right, so today is the first lecture. It may be short, but this is just to get familiar with the setting and get to know you guys, etc. But I will try to finish up this set of slides. But the formal lecturing will kind of start from next lecture. And as I email you all, there are no reservations this week because EAs haven't been decided, and I haven't started teaching anything yet. Okay. So let's see. Okay, so I'll start with the slides. Okay, first a few logistics. So there is a website that I emailed you guys. This is the website where I'll be making all the announcements, all the links, so everything will be there. And I will, in the class, in general, so I taught these with you last time, and I taught a few of the courses, not 215. So generally what I do is I create a Google Doc actually where I make notes, and I may also use an iPad where I may draw things. If there is, Google Doc, of course, I'll make the link available, the Google Doc notes where I make notes. If I do some substantial drawing, etc., I'll make that available also. Everything will be on the website, whatever I make available. Beyond that, yes, lectures. Lectures, I have asked them to record the lectures. I presume that's the camera they are using to record. Last time, I had a 8 o'clock in the morning class. That was 373. That was last semester, and I was recording the lectures and also streaming that live. And out of 100 students, only 5 used to come, which I didn't mind, to be honest. I don't mind teaching a single student. It doesn't matter to me. But then I actually thought a lot as to should I be kind of forcing you guys to come in? I mean, sometimes so I've struggled with this question that, you guys are old enough, why should I be forcing you guys, you know better. So most likely I'm not going to stream live the lectures this semester. Though I haven't made a final decision, but that is what I'm thinking. And the reason is that perhaps you guys are not old enough. Okay, perhaps I need to put some pressure on you guys to come, because I can guarantee you, coming to the lecture certainly helps for many reasons, and you'll see that even if you are, half the time you're not paying attention, even then it will help. So it's always a good idea. And the recording is always there, so in case of emergencies, etc., you can always skip and look at the recordings. And I don't plan to travel or skip a single lecture this time, except maybe one. That is October 29th. I'll try to make sure there is a midterm, etc. But if I do, in some extreme situations, if I have to take a lecture online, that is remotely, if I'm somewhere else, then we will do a Zoom. Okay, and I'll post a link. But I don't anticipate that happening. Maybe once or twice in the semester. Okay. Beyond that, we will of course do things in person. Any questions? So, this is just simple. But what I wanted to get across is 215. How 215 is related to computer science is we are not going to do any programming in this course. Okay, there is very little computer science we're going to see in this course. But it is, as it is called, Foundations of Computer Science. It's actually typically called a discrete maths course. Okay, so we are going to teach, we are going to learn some basic mathematics, basic mathematical formulations and concepts that are very important to actually learning computer science. Okay, so that's the motivation. It is challenging, surprisingly, actually, and I think. So anyway, for that reason, coming to class is very helpful, because coming to class, what happens is one thing that you can ask me questions, okay, which when you're looking at recorded lectures, you don't get that thing. And by the way, I'm extremely I'm extremely patient, or at least I want to think that I'm very patient. So in terms of interruptions, asking me the class, etc., please don't hesitate. And I try my best to be very, very patient, even in office hours, etc., etc. Yes. So, so the point I was making on this challenging bullet is perhaps not accurate. Perhaps the accurate wording would be students find it challenging. Okay, but that doesn't mean you would find it challenging. This is my past experience, but I don't think there is anything very challenging about these concepts. Okay, so we will have recitations, and generally what I'm going to tell the TAs is to basically pick a handful of problems from the textbook and solve it largely. And of course, answer your questions or answer any of your favorite problems. It's possible that I may not tell the TAs exactly what problems to solve, because that's just unnecessary micromanagement. So they may do that. I will probably, of course, ask them to stay away from the homework problems. Okay. So this is how I plan to do the grading. Generally, I have only one midterm, but this time in 215 in particular, I had 2 midterms, and I think that is a good idea to have 2 midterms. It's basically, it's actually better for making you realize, if at all, how far behind you are, how much to catch up, and so forth. So it's always a better idea to. I think it's good to have 2 midterms. So I decided to continue with 2 midterms. So extra credit. So extra credit is something unique to my classes. I don't think anybody else in the department does that, but people have really liked the idea. So I'll tell you what it is about and how it is not going to hurt you and how it is perfect. So basically, what I do is when I'm doing lectures or when I'm teaching, and I'll tell you something about my teaching style also. But anyway, when I'm teaching, I will ask you a question. Question will be related to what I'm doing. For example, I'm trying to prove a theorem. I will ask you guys, can you guys prove the theorem for me? Okay. Of course, I will only ask things that in my opinion, are doable. Okay, by you guys. And of course, I'll give you a few minutes to think, and then I'll some people will raise hands. I'll pick one of you guys, and if you guys answer satisfactorily, then I give you a percentage extra credit. Percentage means essentially percentage of the total grade. That means if I give you 3%, that is essentially 3% of the total grade out of 300. Okay. Now I try to spread it across. That is, if somebody has already answered, I tend not to pick the same person again. So I try to spread it across. That is one thing. Second thing is, some people have complained that because they are shy, they miss out on it, etc. So what I have done as a result of that to address that is that when I grade you guys, I'm not going to look at the extra credits. So basically, the point is the curve, or what I call the cutoffs for the grades, is independent of the extra credit. So extra credit is only used to help some people, not hurt some people. Okay, so it shouldn't hurt anybody. It should only help. And the reason why I have these is not to help you guys. It's actually not to help you in terms of percentage. It's a way to energize the class and to keep you guys on the toes. And it's the questions that I'm asking you are not boring questions. They are mostly, by and large, they're going to be intellectual brain teasers kind of questions, right? So it's kind of brainstorming sessions and so on and so forth. And that gets back to my teaching style. So contrary to what most people do is, in fact, I don't even have slides for 373 actually. And I don't believe in having slides. Here in 315, I do have slides, but I don't have solutions on the slide. So for example, I'm trying to, my slide says, prove such and such. I don't have the proof on the slide. I like to think with you guys on the fly. Okay? And the reason is that, because that is how you're going to learn. If you see a solution, then just explaining the solution, already written solution, I don't think it's very instructive. What is instructive is that we together come up with a proof on the fly that basically tells us what are the wrong ways to think about it, what are the right ways, and why it is right, why it is wrong, etc. And of course, there is a danger to that. The danger to that is sometimes I goof up because I'm thinking on the fly rather than reading on the slide. Okay, and I've accepted that as reasonable side effect. Okay, that's fine. Okay, so that is what I wanted to say about the extra credit, and that we can do things on the fly. Okay, without reading the solution on the slides. So slides generally will not have solutions. We will actually do that, and that is why the Google Doc will come in handy. So the PowerPoint, in some way, the slides are more like the chain of things that I want to cover, as opposed to everything that I will cover. Okay, so there will be a Google Doc where we'll write the proofs. So you have to look at the slides in conjunction with the Google Docs. Okay, yes, so the academic misconduct, of course, that is too obvious, but the details are on the web page, what I consider academic misconduct. In particular, I think everything else is obvious except how the homeworks are treated. In the homeworks, so there's a purpose behind the homeworks. So again, I have gotten positive feedback about the homeworks, not in just this class, but I teach, 532, the databases class, and the algorithms class. I give very tough. I try to give the toughest of problems for people, and there's a reason behind it. The homeworks, I look at them as take-home exams or take-home, where I expect you to spend a lot of time thinking of the problems, and through the problems, learn the material that you have been taught. So, for example, to put it in succinctly, in some of the classes, at least I know databases for sure. If I don't have homeworks, students wouldn't learn even 10% of what they learn. So homeworks is a way to learn, okay? And they are tough. And only tough homeworks will make you learn. And to make it effective, I actually treat them as take-home exams. That is, you cannot collaborate with each other. You can work in groups of 2, okay? And me and TS are there to guide you, absolutely. In fact, and just to give you some instances in the past, I had students go back and forth with me on email for a particular question 10, 20 times, and I'm just basically guiding them. In some way, you may look at it as I'm giving them hints, but actually I'm trying my best not to give them hints, but as to make them discover the solution. But of course, I have to feed them a little bit, right? So the point I'm making is, here you're not alone. You are in conjunction with TAs and me, but not across groups. Okay, so I don't want you to collaborate across groups. And there's a reason behind it, because I really want you to learn. It's not about grading. It's not about how much you score, etc. It's about learning. Okay. And in the end, I just want to give you a little bit of assurance that in the end, I think in almost all cases or all classes, people have been happy with the grades they have gotten. So the point I'm trying to make is, in the end, I am very rewarding of grades. So my cutoffs will be very are in my opinion very liberal. So and most of the time students are very happy. So the point I'm trying to make is that the course may be tough. Maybe the assignments will certainly be tough. But in the end, you will likely be happy with the grades you get if you put in sincere work. Okay. All right. So this is the textbook. This textbook is the one that I've used without much thinking, because when I started teaching it, I didn't want to come up with a new textbook, etc. And it has worked out well. It has a lot of the last 6 years actually. Last time I think I taught it in pre-pandemic, 2015 to 17, I think. So I haven't looked at the latest edition, but I'm presuming that it's an improvement over the previous edition. And I think the name may be different. Speed Maths with applications or something like that. That's fine. Yeah, it's pretty much the same thing. Okay. All right. Okay. So this is just a motivation as to how all the concepts that we're going to learn in 215 come together. So this traveling salesman problem actually is the canonical problem I use to tell somebody what computer science is all about. So let's say, for example, a dentist or my wife is a dentist, or if I have to explain her, or if I had to explain her the first time I met her, or somebody else, this is the example that I use actually to illustrate what computer science is all about, because this is actually easy to understand for a non-computer scientist and to illustrate what computer science brings in. So traveling salesman problem is a problem that, say, we want to find out the smallest route that goes through all the capital cities of US, and how could we possibly solve this? Okay. So there are three possible algorithms here. One is enumerate all possible routes and pick the best. Best means the shortest, right? The second is that you start from some random city, or those 50 cities, and you pick the next based on some condition, maybe the nearest next. So you start from Albany and go to the nearest capital city of another state and keep doing that. And of course, you try not to revisit the cities that you have already visited. So you'll get a 2, right? So that is certainly something that will work. Third is a little complicated, but basically solve the problem for all possible subset of cities. And so basically this means is solve for bigger and bigger subsets. So solve for every couple of capital cities, which is easy, right? You take the shortest route, repeat them. But for every triplet of capital cities, maybe it's simple to solve. Then you can solve for every 4 set and 5 set and so forth. So you can somehow build up your solution. And of course, that's complicated, whatever I'm saying. And we will see, you will see in 373 actually how this can be done reasonably efficiently, but still requires some complicated concepts. So 3 algorithms. Now, within these 3 algorithms, in order to explain, in order to even write down or work it out or define it formally, you need a lot of these concepts that we're going to learn in 215 essentially. One is counting, enumeration. For example, when I'm saying enumerate all routes, how do you do that? Or how many routes are there? Okay, so there's some counting involved, and there are some subsets involved. You have to define some functions, etc. Okay, and the most important or the most complicated of the question is Which of them are optimal? How do you prove that number two? Well, number one is obviously optimal because you're looking at all possible solutions. Number one is obviously optimal. And number two, it's not clear actually. It may or may not be optimal. And in fact, it is not optimal, but it is optimal if there are certain conditions satisfied about how the cities are placed. Number three is actually can be optimal, but it's complicated to prove. Okay, so there are some proof techniques involved. How do you prove number three is optimal? Okay, so there are some proof techniques involved to do that, and that is essentially the purpose of, in some way, motivation for 215. That we want to be able to argue about algorithms. We want to be able to write algorithms formally and accurately, and to be able to argue about their properties, optimality, even time complexity, etc. Okay. All right. So these are the topics I'm going to cover. Okay, and I'm not sure about the last one, counting probability, whether I'll get to that, but we will cover the rest. That is logical conditions and quantified statements. Quantified statements are essentially more complicated logical statements, which is, I think, chapter 2 and chapter 3, I believe. Then chapter 4 is about proof techniques. And the proof techniques, even though we learn in chapter 4, we'll continue to use them in set theory and functions. And induction is a proof technique, actually. It's a very powerful proof technique. I have an example here in the one of the following slides. And induction is very closely related to recursion. So we're going to look at recursion and induction together. And then we'll look at set theory functions. And if time is there, then we'll look at some probability concepts, but I doubt it. There is also relations. So if time permits, I may cover relations and or counting and probability, but I doubt we will have much time after functions. Okay, if we do, then we'll cover one of these three topics: relations, counting, and okay. So variables. This is one of the easiest slides, but still, you know, I think the book says something about variables here. So variables is just one way to write equations where we can actually evaluate the equations in many different ways, or it gives us a way to evaluate the equation in a more general setting. And this is a very simple example that you know, if I want to answer the question, how much does it cost to drive a certain number of miles, where I know the number of miles is 100, that depends on two other factors, which may or may not be known, may or may not be fixed. So you would like to answer that question in a more general way. That is actually 100xy, where x is the gallon per mile for that specific car, for whatever car we're talking about, and price per gallon, depending on what the price in the state and time we're talking about. So variables is just one way to represent something that is not fixed, something that we want to allow flexibility to be to change, so that we can evaluate the equation differently for different variable values. So logical statements, this is actually a good example, reasonable example, and this is the motivation behind why we want to do logical statements. So logical statements is essentially formally representing each of these bullets. All men are crazy. How do I represent that statement mathematically? And the reason why we want to do mathematically is so that there is no ambiguity there. Okay. These statements are largely unambiguous, but it is difficult to answer the last question by just looking at these English statements. It's not easy, of course, even if you can with some effort. There's a confidence missing, and of course, things can be much more complicated, right? So here, actually, perhaps likely the last question can be answered using those four bullet statements. So the way what we are going to do is we are going to learn how to represent these logical these statements in some mathematical form, and how to reduce statements as a result of those what is given to us. One way to look at it is, let's say I want to write a computer program which takes a bunch of these statements and answers questions like that. It's very, very complicated, right? Because you have to, in fact, incorporate NLP, or you have to understand sentences and so forth. Better would be that you actually, but on the other hand, if you were given mathematical statements, then it's trivial to write a mathematical formula. Just a bunch of rules, logical rules that tells you that if this and this is given, then this is true and so forth. So mathematical in some way is an unambiguous language to represent logical statements. And then we combine them with some logical rules that we have to infer perhaps whether a given statement is true or false, depending on what is given. So that is what we're going to learn. And of course, qualified statements is a more complicated version of logical statements, and that involves things like all, there is at least one in such a set and so on. So that is the motivation behind logical statements. That is 2 chapters in the book. I will probably take a few weeks, maybe 4 weeks. 4 weeks, okay? These are more complicated examples of logical statements, which we are going to see many of them, and that in some way exemplifies our purpose. For example, the first statement: for all numbers there exists a number y such that y greater than r. And then the definition of a prime number or a prime test: a positive natural number is prime if it is not divisible by any number less than n, etc. So it's kind of complicated, right? There are conditions within each. It should be a natural prime number. It should not be divisible by any number less than it, etc. And that is a mathematical way of writing it in some way. Okay. For all y between 1 and x, and this is the ceiling, etc. as a way to actually represent not divisible. Okay. That is one way to do it. So. So that's what we are going to learn in this chapter 2 and 3. So proofs. Proofs is actually in some way the most exciting of puzzles, actually, or brain teasers. Right. So so I can sometimes designing proofs of things that are obvious is very interesting and exciting and intelligent. Okay. We will see how to write proof for simple things. For example, one of the things that we want to prove is that square root of 2 is irrational. That square root of 2 cannot be written as x divided by y, where x and y are integers. We'll prove that actually very formally. Okay, and that's not very obvious at all actually. So there is Our goal in this chapter is not to teach you proofs of certain statements. That the goal is not to teach you the proof of square root of 2 is irrational. No, the goal is to learn ideas and techniques to prove statements in general, and that is why the real test will be when you will try to prove things in the homework and in the exam. So we will look at some standard proof techniques. And what exactly does a proof mean, and when is a proof considered solid or foolproof? Okay. So here, students generally struggle, and of course I should talk more about it when you get to that chapter. But students generally struggle in trying to be formal, in the sense they will, in the exam or in the homeworks, I've written things like, they will write some paragraph, right, which is in my opinion, certainly very ambiguous and not formal. It's hand waving, but they may think it's solid. So that is one of the things that we want to learn. That for you or yourself to be able to judge what is hand waving and what is solid. Okay, and once you know that, then you will be able to write things that are solid. It's a very, very important skill to have. As a mathematician, for a mathematician, of course, it's the most basic skill to have. And computer science is pretty much, I always think of computer science as part mathematics. So for computer science also, it's a very basic skill, very important skill to have, to be able to prove things. Okay, so these are some examples that we would prove, and we should be able to prove that is any number greater than 1 is divisible by a prime number. Now none of them is very obvious. For all number n, if n is even, then n or n plus 2 is divisible by 4. Then there exists a number n such that n squared by minus 3 is divisible by 7. Okay. So these are just some examples, just to let you know that there are these statements that are not obvious at all, but to prove them, what would be considered as a solid truth. Okay. And we do many of these. So mathematical induction. This is one slide that was missing actually in the if you looked at the slides a couple of days earlier. I just added it last night. This is a very powerful proof technique, and again, this is one thing that it is still a mystery to me why students struggle getting it. Really, it is something that is very, very mysterious to me. But to me, it's very simple to understand, but still, for some reason, students still struggle. But this is my very brief take on it. Just to give an introduction, I don't want you to understand what mathematical induction is in this one slide. But basically, mathematical induction is a skill, or it's a tool to prove something. Okay, and it makes proving something much easier than otherwise. Like for example, this, right? So I want to prove that 1 plus 2 plus 3 up till n is n into n plus 1 by 2. Does anyone know how to prove this? There is a very simple proof of it, which what I have is not the simpler one. This is slightly more difficult than the simple one I have. Does anyone know a very simple way to prove it? Kind of a slightly tricky way to prove it. Yes.
Add it to yourself in reverse.
Yes. So you basically write the sequence in reverse, and then you just add the corresponding number. So you have 1 plus 2 plus 3. And the story that I heard is, Gauss, he was sitting in the back of the class, and the teacher, at that time the formula was not known. So the teacher gave this as an exercise. So we were, hey, why don't you add up 1 to whatever 100 or 1000 actually? And then Gauss, after a couple of minutes, he raised his hands and he surprised the teacher with the way he solved it. So you basically just reverse the numbers. There was a sequence or something. And each of these numbers, they add up to the same, n plus 1. Right? Because one is decreasing, one is increasing. Right? And this is n times. So this actually is n into n plus 1. And because there are 2 of them, you need to divide by 2 to get the summation of one of them. Right? So that's a very simple proof. Well, this is a very simple derivation of this thing. Of course, it's not as simple when I square them up, right? If I'm trying to do 1 square plus 2 square plus 3 square up to n square, this trick is not going to work. Right? Then we need some more sophisticated trick. And of course, you can go to cubes and etc. So generally, up to cubes, etc., we know the formula. In fact, I also know it. Up to 4, for powers of 4, powers of 5, things get more complicated. Anyway, but each of those has a simple mathematical induction proof. The mathematical induction technique is, let's say I know the formula. n into n plus 1 by 2. Somehow, somebody gave it to you. Now, I'm not looking for a formula. I'm only trying to prove whether the formula is correct or not. Right? That is when mathematical induction can come in. Mathematical induction is not a way to derive a formula. It's a way to prove a statement. Okay, the statement has to come with a formula. Otherwise, I will not be able to do it. But this technique that I have written in short will work for, you give me any statement. Well, it doesn't work for all possible formulas and all possible equations, but will work for squares and cubes and so on and so forth, if you give me the formula. Okay, so the trick is the following. And of course, there is one statement missing that you need to show it that it is true for n is equal to 1. It is true for n is equal to 1, right? So if n is equal to 1, then I'll get on the right hand side, I'll get 1 into 2 divided by 2, which is 1. It actually also works for n is equal to 2, right? For n is equal to 2, the answer is 3 on the left hand side. On that side, it is 2 into 3 divided by 2, that is 3. So of course, it is true for, the statement is true for 1 and 2. Now the proof says that, I'm going to just assume by magic, as if God told me, that it's true for some value k. K is some integer. I don't know what that integer is. It could be anything. It could be 100, it could be 200, it could be 300. but it's some fixed integer. I assume it to be true. And then all I'm going to do is, with that assumption, that means with that given equality, I'm going to prove it for k plus 1. That is very easy, right? To proving the original formula is very difficult. How do I do that? Of course, let's say we don't know this, or at least this is not going to work for squares. So proving the original formula is very difficult, but proving it for k plus 1 given k is actually very easy, right? And once you do that, the mathematical induction technique says you're done. And the reason why you're done is, and again, here I'm jumping the gun and I'm telling you, I'm trying to teach you what mathematical induction is all about, but let me complete the slide, right? So the reason why it is done is because you prove the statement to be true for 1. Okay? Then you can use this implication, that is, given k, given the statement is true for k, it is also true for k plus 1. You can use that implication to know, to show that it is also true for 2 then, because if it is true for 1, it must be true for 2. And you can keep doing it. If it is true for 2, it has to be true for 3. And so on and so forth. So there is this domino effect. And this domino effect will go on forever. So in some sense, this mathematical induction, where you have actually proved it for a small number, and then assuming it for some k, you have proved it for k plus 1, then you can use this domino effect to essentially claim that we have proved it for all natural numbers. So that is what mathematical induction is. Again, this is not the time to teach you what mathematical induction is. We will spend much more time when we come to that. But I thought this I should give you some introduction to it and complete the introduction by giving you the philosophy behind it. And it makes things very, very easy sometimes. There are very, very difficult formulas. For example, for the square, there is a formula for squares actually. I think it's n into n plus 1, something like that. So basically, let me see, and I can check it easily. Is actually, let me make sure it is correct. Divided by, I think it's 6. Let me check. If n is 1, what do I get? I will get 1, 2, and I'll get 3 here, right? Yeah, so that seems correct. Let me try for n is equal to 2. N is equal to 2, I'll get 2 times 3 times 7, right? No, 5. Divided by 6, so it's 5. And this is also 1 plus 5. So that formula is actually correct for squares. Now, proving that formula from scratch is very difficult. I actually, myself, wouldn't know how to do that, actually, to be honest. At least it doesn't come to me. But mathematical induction, it's very easy. All you got to do is you got to assume that this is true for k. That is basically 1 plus up to k squared is this. You assume this to be true, and then you show that this is true for k plus 1 squared, which basically means that you need to show that. Again, I'm trying to solve mathematical induction problem, but hey, you know what? You don't need to understand it, but at least some of you will get it. You need to show that this is equal to the appropriate formula for k plus 1, which essentially means that you need to show. So you already know what is this. This is actually k into k plus 1 plus 2k plus 1 by 6 by assumption, and you add k plus 1 the whole square to it. And what you need to show is that this is equal to the formula for k plus 1. What is the formula for k plus 1? Well, let me write it down. If I put k plus 1 here, I'm going to get k plus 1 into k plus 2 and into twice of k plus 1 plus 1 divided by 6. I need to prove this. This is trivial. This is trivial. You can just expand it and subtract things, and you will see that this turns out to be true. This is very trivial. So the proof boils down to proving this, which is trivial, which is simple. This is like a 2-minute job. Any student can do this. So this is just a way to show you how powerful mathematical induction is. That otherwise that formula is very complex. I actually don't know how to prove that formula. Actually, I myself don't know how to do it. At least nothing is coming to my mind. But mathematical induction makes it very trivial. So mathematical induction is like a mathematical technique, a proof technique to prove certain properties. but it only works for integers. That is, to apply this cascading effect, you must be going through some integers. So it only works for properties involving positive numbers, okay, or negative numbers. But anyway, so that's just one brief introduction to mathematical induction. We will see much more of it when we come to that. But this is something that I really want everyone to get, and we will do some very, very interesting examples involving it, and we'll see how fun it is. Okay, any questions? No questions? Okay. All right. So once we have learned the proof techniques and mathematical induction, and by the way, with mathematical induction, we are also going to learn recursion and yes, so we are also going to learn recursion there, which I will talk about. Okay, so then we'll move on to sets. Sets is, I believe, chapter 6, I believe, yes. So sets is basically, I would say it's a simple topic. It's nothing complicated, but where the complication will arise here is again trying to prove things about sets. So in some way, set theory, most of the things will be simple, but the things which will be challenging will be proving things. In some way, it's like a playing ground for the previous topics that we have learned. So set theory will be basically a concept or an underlying theory where we will make use of our proof techniques. That is where it will become challenging. Otherwise, beyond that, set theory should largely be something that you perhaps already know or similar. Okay, but of course, we will do it extensively that maybe we will learn some things that you guys don't know of before. There's just some simple introduction to set, but basically we will prove things here. That's when things will get challenging. Okay, so here we'll look at various relations and operations over sets, and some new concepts, perhaps Cartesian product or a pair. And we need to understand this actually in order to look at functions and relations in the next chapters. So set theory is important to know to be able to understand functions and relations. Okay, so again, these slides are not meant to teach you concepts. These are just to give you a flavor of what this course is all about. So if you don't understand, that is fine, but the goal is to give you a flavor of what we are going to learn throughout this class. Okay, and how, in some way, to motivate each one of these topics and how they tie together, and to give you an idea of how exciting it is going to be. Okay. Now, relations and functions. So relations is related to functions. So functions is something we'll certainly cover. We're not sure relations we'll cover in detail, but relations is an important concept. It's basically some way if you're given two sets. Relations can be looked upon as a relationship or association between these two sets. For example, if you have a set of drinkers and a set of beer, and this is actually my most popular example from the database class. That is, of course, the textbook I use also uses that example. And in the databases class, I use this drinkers, beers, and bars, these three sets. And just with these three sets, we have so much fun with SQL and create such complicated examples of SQL that actually works very well. Anyway, so here I've used the same example to define this concept of likes, the association of likes. So I want to represent the concepts that certain drinkers like certain or some of the beers, right? So how do you represent the concept that I want to represent this relationship between drinkers and beers? One way is you represent all possible pairs, right? Which are true, that drinker 1 likes beer 1 and beer 2 and so on and so forth. Or this is just a pictorial representation of what I'm talking about, that you have these lines, segments. The arrow may not mean much, but these lines that are associating drinkers with beers. So it's just two sets and some lines connecting elements from one set to another. And that is exactly what a relation is. Relation is just a set of pairs from two sets that are somehow related by some association name. here it's likes. So this is an example of a relation. Okay? And there's no constraint on how these lines can be. One drinker can like 5 beers, 6 beers, 2 beers, or no beer. And a beer can be liked by multiple drinkers or no drinker, right? So there's no restriction on how these lines or associations can be. Okay? And so there's another way of writing it, just a bunch of pairs. In general, it is, well, you can ignore the last sentence if you don't know what a Cartesian product is. So S1 times S2 is actually a Cartesian product of the two sets and just a subset of that. So the blue sentence may not be very, because we haven't learned these concepts, but basically that is what a relation is. Now, functions. So functions are a specific type of a relation. One way to look at a function is a special case. It has some restrictions on what these lines are. Okay. For example, if I look at the married to relation, right? So then what will happen is, and if I have two sets, married men and married women, how would this look like? Now, married to, I want to go from, let's my married to is from men to women, as opposed to, I can also look at the reverse relation, which it shouldn't matter actually. So let's look at the relation with the direction of the that men to women for a minute. How would this relation look like? That each man here in the set married man will have exactly one line coming out of him, and he will have exactly one line because everybody is married in that set. So he has to have one person who is married to, and only one line because we live in a monogamy system, right? So so this is also a relation, except that it has some constraints, or it has some properties. The properties is that each element of LHS is related to exactly one element of RHS. Such a relation is called a function. That's basically what a function is. Function is essentially imposing a condition that the relationship is that for the input, each input element has exactly one output element it is associated with. Okay? Now, in this case, of course, the reverse is also true, but in general, for a function, the reverse may not be true. And the next slide is essentially talking about giving an example of that. Yes. If I look at this example between children and men, each child has a father, exactly one father, right? And some men may not have any children, right? So there could be some men who don't have any father, but still, this is a function. Because the only condition that we are requiring is that each element of the input set has exactly one association, and multiple children can have the same father. So this is what a function is. So this is just to tell you what a function and a relation is. Relation is basically a general association. Function is an association with some restrictions. And why do we learn that? Because it's extremely important. It's extremely it's a very basic concept of mathematical language to represent things. Okay, for example, we talked about trivial salesman problem, right? So there we need a function. We need a function that tells me that for a given route, what is the cost? Okay, so the function could be from route to a cost. Okay, each route is going to have exactly one cost, right? But every route will have. So a function is extremely important. Okay, it's a very basic tool of mathematical language. That's just a diagram, but essentially saying that there is a rotation, and basically look at you can look at function as some machine that is basically churning out the output, one output for any given, and it has to take some output. This is some example. It's not very important, but let's look at this example. So let's look at the second set of examples. We have functions from people to people. So best friend of P is a valid function. Father of P is a valid function because everybody has a father. Spouse of P could be a problematic function because not everybody has a spouse. There are people who are not married. So the third function is not a valid function because some of the people may not have spouses. So the third is not a function. Fourth one, front of P, is not a function because one person can have many fronts, and the function requires you to have exactly one output. Okay. Anyway, again, I just want to repeat that this is not to teach you functions and relations. This is just to give you a flavor. We will learn about this much more detail when the class comes, when the time comes. That's it. And this was my last slide. So, any questions? And again, today's lecture is short. You just get to know each other, you get to know the class. Any questions? I'm here for another 5 minutes. Yes. Yes, I have put it on the.